Grid Map. And it's a shared work between Aarhus University and Bielefeld University in Germany. So the motivation for doing this lies within autonomous farming or autonomous agriculture. So it's a concept of self-driving farming vehicles that need to be efficient and reliable, of course. So it could be a tractor or a harvest or a small robot operating in the field. But what we are most concerned with is the safety. So in order for these farming vehicles to be safe, they need to, of course, avoid any potential obstacles in the field. It could be humans, it could be animals, or anything else really that it can harm. And in order to achieve that, we need to make them perceive the environment, to have a number of sensors and accompanying algorithms that can detect these threats or obstacles. And in this work, we have focused on a mapping approach where we try to do global mapping in the field. So we actually put in a 2D grid on the field and then regard each cell in that grid as being either occupied or unoccupied. So in this case, where we have a small animal, these cells would be occupied, whereas anything surrounding that would be unoccupied. And in our work here, we are only looking at static obstacles. We don't look at moving objects. That's something that we'll focus on in the future. Okay, so what we did was last year in Falun here in Denmark, we went to a field in a grass mowing scenario. First we overflew the field with a mapping drone where we had placed a number of static obstacles. So we had a number of wells on the field. We had some mannequin dolls acting like humans. And we had a number of barrels and a vehicle placed on the field as well. And of course some surrounding trees that are of course also obstacles. And then we traversed the field with a tractor going from one end to the other and recorded with a number of sensors. So this is the setup that we used. We had a number of sensors mounted on a tractor. We had GPS, RTK GPS, and an IMU, that's an inertial measurement unit that can measure position and orientation. So that provides us the position or the localization of the tractor during the traversal. And then we had some perception sensors. We had a normal color camera, just a webcam, an automotive radar, and a lidar. And that's an abbreviation for light detection and ranging. It functions just like a radar. It just uses laser light instead. So it gets measurements distributed around the vehicle of the range to those to the environment. So in order to do this, we started implementing a number of detection algorithms. So we wanted to detect all these different obstacles. And for the camera, we implemented 3 state-of-the-art object detectors. So the first one is a pedestrian detector. We want to detect humans. And as you can see on the upper figure here, it's able to put a bounding box around the 2 humans. So it's able to detect humans, of course. The next one was a general object detector using deep learning. So that was trained for detecting a few other categories, humans, cars, and a few other object categories. And the final one uses pixel-wise detection, again with deep learning, so that you can see on both images here that for each pixel in the image, we actually classify that pixel as one of these 7 classes. So we can say if it's ground, or if it's sky, or if it's a vehicle, or trees, again using deep learning trained on a huge data set. Then for the radar, it actually provides detections, but we needed to perform some further tracking. So we implemented global nearest neighbor tracking and are then able to detect structures like the trees here. There was a human up here we detected, and also the car that we pass on our way. And for the lidar, we get a point cloud. So these are point measurements distributed around the vehicle as we traverse the field. And for each point, we calculate a number of features using the surrounding points. And based on those features, we can then estimate the probability of that point being just ground, something we can traverse, or being an object or an obstacle. And this video actually shows the probability of every point being an object. So the tractor is rather red in this video, illustrating that it has high probabilities of being an object, whereas the ground is quite blue, meaning that it has low probabilities. And all these outputs of all these detection algorithms are then put into a mapping framework. And that's where we use something called occupancy grid mapping. And basically, this is the basic update equation of the occupancy grid mapping algorithm. So what it does is that it tries to estimate the probability density function over all cells. So all cells in our grid of the environment, we want to estimate the probabilities of occupancy or not being occupied, given all previous measurements. So that's set, and that comes from the detection algorithms, and all previous poses. So the occupancy grid mapping algorithm actually assumes that we have a known pose. And that's where we use the GPS and the IMU sensors, where we fuse the measurements of those with a carbon filter to provide rather accurate pose estimation of the tractor. And then we can put that into a map that we continuously update. So actually this is a recursive formula. We can do that as we traverse the field to continuously know what objects or obstacles are out there. In order to put that into the framework, we need a common representation for all sensors. And that's called an inverse sensor model. So it's actually a mapping just from raw sensor data to a 2D grid in the vehicle frame. So a top-down view on the vehicle. And for the lidar and for the radar, that's rather simple, since both sensors operate in Cartesian metric coordinates. So it's actually just a matter of projecting down to 2D. And that's what we see here, where we have a 2D probability grid for the lidar, where each cell has a probability of being occupied, and that can then be put directly into the update algorithm. But for the camera, it's a bit more troublesome, because we can't just do this directly. We need to make an assumption, and in our case, we've made an assumption that we have a flat ground plane. And when we do that, we can then use something called inverse perspective mapping. So what we do is we have a raw input image, in this case of a car. We then use one of the detection algorithms, in this case the pixel-wise detector, that is able to detect the car. And then we perform an inverse perspective mapping to sort of simulate that we look at a top-down view of this car and then get the probabilities of the cells being occupied by the car. Then we want to fuse all these different algorithms and all the different sensors. And we do that in 2 steps. First, if we look at a sensor here, it could be the camera. The camera has a number of classifiers, so it's able to detect pedestrians, vehicles, trees, etc. And first we fuse across those different layers. And we do that with something called competitive fusion, and in our case we use a strategy called maximum fusion. And we do that for all the 3 different sensors. And once that's done, we can then fuse on the next level. So now we want to fuse the different sensors. And we do that with something called complementary fusion, with super Bayesian independent opinion pool. And the output of this fusion stage is then an obstacle representation, a binary obstacle representation. Now we don't care if it's vehicle or human. Now we only want to look at if it's occupied or unoccupied. And when we do that, we can evaluate, or we've evaluated 7 different setups. So the first 3 setups are just the 3 different sensors individually. So we wanted to look at how good can we do mapping with just a camera, with just a lidar, and with just a radar. And then the next 4 are combinations of these sensors. And we've then evaluated it on precision, recall, F1 score, and accuracy. And just to jump to the conclusion, we can see that the best mapping performance is achieved once we combine all 3 sensors. We can see that we get the best F1 score and the best accuracy when we combine all 3 sensors. And that's actually also what we hope for, that adding more information, adding other modalities increases the mapping performance. As you can see, it's only marginally better than the lidar, but still there's a small improvement. And if we look at that visually, we can see here, as we traverse the field, we can build up this map. The different colors correspond to different object categories. So the green here is vegetation coming from the lidar, the dark green is vegetation coming from the camera, and there are a few other categories as well. Human here, and there was a car before, the red part. And the great thing about this is that we can do it online. So the occupancy grid mapping algorithm allows us to put information continuously as we traverse the field, so that we continuously update the position and the occupancy of the different cells. So the conclusion is that we've come up with, or we've tried the global mapping approach in agriculture, implemented a number of detection algorithms for the camera, a radar and a lidar, and represented that with a 2D grid representation where each cell is then occupied or unoccupied, and fuse the different detections and the different sensors using competitive and complementary fusion. And this is actually the result once we traverse the field just once, where we can see all the white pixels have been marked as occupied and all the dark ones have been marked as unoccupied. That's something we can traverse. And we have a combined mapping accuracy of 96% when comparing to the ground truth that we have from our drone recording of the ortho photo that we generated with the mapping drone. And future work will focus on dynamic obstacles. We also want to include moving humans, animals, other vehicles. Right now we only have a static map. And then also to train the optimal fusion of all the sensors. Right now we do it quite naively in that we don't weigh the different sensors corresponding to how trustworthy they are. And finally, we'd also like to extend the evaluation. Right now we're only doing this on a single field. We'd like to extend that to multiple fields, multiple environments, seasons, etc. So, thanks for listening.
Mr. Kragh, thank you very much for what you present starting on vision. Now, do we have any questions on this? Okay.
Did you test the new ship camera time of flight capable to discriminate up to 30 obstacles, static and dynamic obstacles?
We haven't tested the time of flight cameras. Do you think of a specific sensor or?
Wait, there are some on the market.
Okay. Yeah.
Camera time of flight for safe purposes in industry, agriculture, and so on.
We would like to look into it. I think, or I've heard that time of flight can be an issue when you have direct sunlight. There's something about the range in direct sunlight, but and the layer, at least the lidar that we use is much more robust towards those changes. But yeah, it's something relevant to look into.
Any questions? Okay.
Sorry, does the system that you developed can recognize the mobile objective, like the animals or human in the farm?
If we can locate moving objects?
Yeah.
Not yet. Not yet. Not with this approach. There is a standard or an extension to occupancy grid mapping that can do that. Then you actually generate a static map and you generate a dynamic map. It's called a velocity map. So it has been done before. I'm not sure it has been done within agriculture, but it is something that can be done. But we haven't included it in this study.
Okay. So, another question? Okay, thank you very much.